In sections 4.3 and 4.4, we're looking at some shortcuts for proving triangle congruence. So in the side-side-side congruence postulate, which we will just call SSS, where S stands for side, we use this when we know all three sides of both triangles. So in this postulate, if three sides of one triangle are congruent to the three sides of another triangle, then the triangles are congruent. I want you to work the examples in your notes. While you do, please pause the video. When you have completed these examples, please resume the video and I will go through the answers. In example A, we have 1, 2, 3 pairs of corresponding sides that are congruent. So we do know all three sides of both triangles, and so the answer to this one is yes, these two triangles are congruent because there are 3 pairs of congruent sides. And the other thing you are supposed to do in your notes is to write a congruency statement. So remember, it doesn't matter which order I write the 3 vertices of the first triangle, so let's call it triangle PQW, for example. And that is congruent to my other triangle, and now I have to list the corresponding sides. So angle P is between my blue and my green mark, and so is angle T. And then Q is between blue and yellow, so is S, and then the remaining one is W. For example B, I again have 1, 2 pairs of congruent sides, and then it's a little bit of a hidden thing, but side LM is on both triangles, and because of the reflexive property of congruence, it is congruent to itself. So the answer to this one is also yes, because we have 3 pairs of congruent sides. Again, we need to write a congruency statement, so let's just do KLM is congruent to my other triangle. So K is going to correspond with N, and then L actually in my second triangle corresponds to the same L and then the same N in this particular case. Okay, just be careful, L and M may actually not correspond to each other in different triangles depending on how those sides are arranged. Here's an example of where you may see the SSS postulate, which we are just going to abbreviate as SSS in our proofs. So here's an example of that. So we are given that C is the midpoint of AE, and so that is our first statement. So let's go ahead and mark that so we know we have some pairs of congruent sides. So that's going to actually be our next statement, is that segment AC is congruent to segment CE. And so my first statement was given, and this one is just going to be because of what the definition of midpoint. So if it is in the middle, it divides that total line segment into 2 congruent segments. Now, it is also a given that C is the midpoint of segment BD. So each of those, and we'll use 2 hash marks in case your color is not showing up. So those are also congruent. So those are segments BC and CD being congruent. And again, that is just because of the definition of midpoint. Now, we know that we want to prove that these 2 triangles are congruent, so we have to have 3 pairs of matching sides based on what we have so far. Now, in this case, we have one more given that we haven't used yet, and so that's going to go here, and that is that AB is congruent to segment DE, and so that is this side and this side. So I do have 3 corresponding sides, so I can prove this statement using the side-side-side postulate. An important vocab word for this unit is an included angle. So an included angle is between 2 adjacent sides of a polygon. In this section, that's usually going to be in a triangle. For example, angle A is included between the sides AB and BC. So when I'm naming the segments, the shared vertex is going to be listed hopefully in both of those. So you may be able to look at that and see if our angle is going to be an included angle. Again, we're going to work the examples, pause the video while you do, and then resume it when you have your answers. For example A, we are told that WX and XY are what we are looking for the included angle. So that is right here. That vertex is X, so we can call this just angle X. In example B, we're looking at the angle included between XY and YZ, which is this angle here, and so that is angle Y. Our next postulate is side angle side, so we need to know two sides, and because the A is written in between, it is the included angle between those two sides. Again, this postulate says that if we know two pairs of congruent sides on two triangles and the included angle on both triangles, then using SAS, we can pronounce these two triangles to be congruent. Both of these examples have a missing third congruence statement that needs to be given in order to prove that these two triangles in each figure are congruent by SAS. So, work your examples with the video paused and then resume when you're ready for the answers. In example A, we are told that segment WX is congruent to segment YZ, and we are told that segment XWY, which is this angle, is congruent to angle WYZ. So that is this angle. Now, in order to use SAS, that angle needs to be the included side, or the included angle. So if I was just going to trace from this side and then cut around that angle, okay, and do the same thing on this triangle, then I am missing right here, that needs to be congruent. And so the statement is that that is the same line. So in this case, we can definitely make that statement and say that segment WY is congruent to segment WY by the reflexive property of congruence, but that is the one that we need in order to finish out the SAS postulate. In example B, we are told that WX is congruent to YZ, and we are also told that YZ is congruent to XY. Now, those are two sides, so I need the angle that is included in between them. So in this case, I need these two angles to be congruent. So the statement that we need is that angle X is congruent to angle Z. In our next two examples, you are deciding whether each set of triangles are congruent and justifying your reasoning. If possible, so if they're congruent, write a congruent statement. Again, work these with the video pause and then resume when you're ready for the solutions. We are given that Z is the midpoint of XQ, meaning that these two segments are congruent, and Z is also the midpoint of YP, so these two segments are congruent. So we do have two sides on each triangle that we know. We don't know the third side to use SSS, but this angle here and this angle here are vertical angles, so we know that they are congruent. And so these triangles, so triangle X, Y, Z, is going to be congruent to triangle QPZ because we have side, angle, side. In example B, we are told that these two sides are congruent, and then all right angles are congruent to each other. They're all 90 degrees. So we have a side on each, and we have an angle, and then we know that this side is congruent to itself, but here I have a side, and an angle that is not included in each triangle. So based on what we know so far, the answer is no, these triangles aren't necessarily congruent. However, there is another postulate that we are going to use, and in that case, it has to deal with when I have a right triangle, and so let's cover that and then come back. So there is another theorem called the hypotenuse-leg theorem in this case, not a postulate, and so this applies when we have two right triangles. So we must know they are right triangles, and then we must know the hypotenuse on both and a leg on both triangles. If we know that the hypotenuses are congruent and there is a pair of corresponding legs that are congruent, then we can use the hypotenuse-leg theorem. Remember, hypotenuse only applies in a right triangle, and so does this theorem. That does mean that in our previous example B, where based on SSS and SAS, the triangles were not congruent, we do know with the addition of hypotenuse-leg that we can actually say that those two triangles were congruent. We aren't going to do the proof of this theorem now. We will come back to this in section 4.6. So that is where you will find this piece of information in your notes. Before we go on to do any more problems, I want to point out that sometimes there are some things that are given to you in the diagram, even though we can't call them a given. They are shown to you and they aren't explained explicitly to be true. So one of the first things is that vertical angles are congruent. So if you see that, the reason in a proof is you can just write this statement right here. Vertical angles are congruent. You don't have to remember the name of that theorem. Okay? The other thing is that shared sides, so if a side is in both triangles physically, okay, it is congruent to itself, and the reason for that would be the reflexive property of congruence. Okay? And then, if you are told that there are parallel lines in your diagram, you can then sometimes find angles that are congruent. So in that case, the things you would write would be alternate interior angles are congruent, corresponding angles are congruent, or you could write alternate exterior angles are congruent, but most likely, the one that you're going to use most often in triangle congruence is alternate interior angles, and you would just write alternate interior angles are congruent, and that way you don't have to remember whether it is the theorem or the converse of the theorem. You can just make the statement that alternate interior angles are congruent when formed by parallel lines. So let's look at how that looks in action. So we are given that AC is perpendicular to BD, and by the definition of perpendicular lines, we know that the angle formed is a right angle. We are then looking at angle BDA, which is here, and BDC, which is the one that is marked. Well, so this is, if I have 180 degrees for that total line, and I know that one of them is 90 degrees, so we know that this other one has to be 90 degrees, and they are congruent, and you can say that is because all right angles are congruent. Now, we did learn this as the right angle congruence theorem back in chapter 2, but if you just write the statement that all right angles are congruent, that will also suffice as a reason in a proof. Now, our next line, statement 4, that AD is congruent to DC, that appears up here as a given. And then the fact that BD is congruent to itself, that reason is the reflexive property of congruence. Remember, you can remember it as reflexive because it's like looking at your reflection in the mirror. You're still seeing you. Okay? So now we have two shared sides, or we have two pairs of congruent sides, and we have the included angle. So our reason here is going to be two sides with an included angle, SAS. So just like an angle can be included, we can also talk about the included sides. So the included side is between two consecutive angles. For example, if we have So we need to know the included side in order to use our angle, side, angle congruence postulate. So this is when you know two angles and the included side. Again, if you know two angles in both triangles and the included side is congruent on each, then by angle, side, angle, you can declare our two triangles to be congruent. You're going to use this example to find the third congruency statement that must be true, that must be given in order to prove that these two triangles are congruent by angle, side, angle, if angle A is congruent to angle D, and if angle B is congruent to angle E. Go ahead and come up with your statement. If you need to pause the video while you do that, please do, and then resume when you're ready for the solution. For angle, side, angle, we must know two angles and the included side, so you can see it's written in between the two angles. So the sides that are in between, that are our included angles, our included sides here, are segments AB and segments DE. So we must know that they are congruent in order for these two triangles to be congruent by ASA. So here's what that might look like in a proof. So we are given that BD is congruent to BC. That's a given statement. And we are also given that line AD is parallel to line CE. So again, those are actually in the picture as well. They are marked. So that is another given. And then we are going to say that angle D is congruent to angle C. Well, that's not in my given statement, so let's draw ourselves a picture here. So if I have two parallel lines, and then line CD would be my transversal, so these are alternate interior angles, and we know that alternate interior angles are congruent when lines are parallel. So you don't have to remember whether it's the theorem or whether it's the converse, just write this statement, and it is a valid reason. Okay, the next thing is we are told that angle ABD is congruent to angle CBE. So this is another one of those hidden given statements in the diagram. So those are vertical angles, and we know that vertical angles are always congruent to each other. So again, you don't have to remember the theorem name, but you can just write vertical angles are congruent. Okay? And now, looking at our diagram, we have an angle and an angle in both, and the included side in both. So our reason to say that our two triangles are congruent is angle, side, angle. Our last congruence theorem is angle, angle, side. So when you know two angles and a non-included side, all right, we also are able to say that our triangles are congruent. So we're going to skip the proof for this one, so you can skip this in your notes, okay? And we're going to jump straight into using this in our example problems. Again, we're skipping the proof. These two triangles, we're going to use the diagram to find the third congruence that must be given in order to prove that these two triangles are congruent by angle, angle, side, if we are given that angle A is congruent to angle D and side AB is congruent to side DE. Again, if you need to pause the video while you work through this, please do. So for angle, angle, side, the other angle that I know cannot make our known side be included. It needs to be on the other side. So if I was going to go through, it needs to be angle, angle, side. Well, right now I have angle, side. And so what I need is I need another angle, but I need to go this way around the triangle. So I need angle C to be congruent to angle F. So here's what a proof using angle, angle, side may look like. So our two sets of perpendicular lines, so VW and VY, okay, that's a given. And then YZ and VY are perpendicular. So those are pairs of perpendicular lines. So we know that angle V and angle Y, you might have noticed I drew them in as right angles, and that is because of the definition of perpendicular lines. For angle V and angle Y to be congruent to each other, that is because all right angles are congruent because they're all equal to 90 degrees. Okay? Our next statement that VW is congruent to ZY, that is a given statement. Okay? And then we are looking at angle VXW, which is right here, and angle ZXY, which is right here. And the reason for that is that vertical angles are congruent. And so now we know an angle, side, and an angle, side in each triangle. So that is our reason for saying that our two triangles are congruent. In summary, we learned 4 theorems and postulates in 4.3 and 4.4, and we added in HL, which actually doesn't come in until 4.6, but for our purposes, we're going to lump it in. So we have 5 total postulates and theorems to prove that triangles are congruent. You should memorize these, but all you have to really memorize is the names in acronym form, so you know that you need 3 sides, or 2 sides and an included angle. Okay, so the names give you what you need. Also remember these things, okay? So we have our hidden congruency statements, vertical angles, a shared side is the same as itself, and when we have parallel lines, we can use our things from the second test in chapter 2. So usually alternate interior angles, but don't forget there are others, okay? And then there are 2 other ways that we could know sides and angles, which you may have been going, well, what about those? So side angle, so 2 sides and a non-included angle are not necessarily congruent. We're not going to prove why, just know you can't use it. And then angle would give us always 2 similar triangles where they have the same shape, but I could scale one triangle bigger or smaller to be the same as the other one, and so angle doesn't tell me that my triangles are necessarily congruent, okay? So you cannot use those 2 methods, okay? For our last 4 examples, for each of them, you're going to state the postulate or theorem that can be used to conclude that the given triangles are congruent. So please work these with the video paused, and then, when you're ready, resume for the solutions. In example A, we have 2 sets of parallel lines. So we have that AB is parallel to CD, and then we have BC is parallel to AB. So then segment BD cutting across our parallelogram is going to be the transversal for both sets of that. And so we can say that angle ABD is congruent to angle BDC because they are alternate interior angles. And then we can also say that angle ADB is congruent to angle DBC because they are also alternate interior angles. And we can say that this segment is congruent to itself. And so I have 2 angles and the included side, so that is angle, side, angle. For example, B, which is the one below that, we know that we have this angle and this angle that are congruent, and we have this side and this side that are congruent, so those are told to us. And then one of our hidden givens, remember, is that vertical angles are congruent to each other. So now I have 2 angles and the non-included side, and so angle, angle, side is our postulate or theorem. In C, we're told that we have a matching pair of congruent sides, we have congruent angles, and then again, we know that this side is congruent to itself because of the reflexive property of congruence. So now we have two sides and the included angle, so that is SAS. And then finally, in example D, we know that this side and this side are congruent, and we know that this and this are congruent, and we know that a shared side is congruent to itself, and so this is going to be side, side, side.